I think we're going to get started. So thank you for everybody for joining today. So Atmosic is going to plan a series of webinars. This is our first one. Hello, my name is Will Carr with Atmosic Technologies. I'd like to welcome you today to today's webinar. We're going to focus on energy harvesting techniques for PV, RF, thermal, and mechanical energy. We'll review each harvesting method independently, and then we're going to review how Atmosic can utilize each of these methods to build sustainable IoT products that can extend battery lives forever or allow for battery-free applications. Paul Davis, who's our Director of Product Marketing, will review these solutions today. During the meeting, please feel free to ask questions in the chat session. At the end of the session, we'll respond to those questions with additional help from our co-founder, Masoud Zargari, as well as our Senior Director of Technology, Paul Husted. I'd now like to introduce Paul Davis, who will take us through today's presentation.
Thank you, Will. Good morning, good afternoon, good evening, everybody. Hopefully you can all see the slide that's up there. So as Will was mentioning, I'm going to walk you through a little summary of various energy harvesting technologies that we see for IoT applications specifically. So let me move forward here with the presentation. So I think anybody who's been involved with IoT is very well aware of the huge market opportunity that's there. We're talking about literally billions of devices that have already been deployed in the field, and the projections are in the tens of billions of more devices that are going to be deployed over the coming years. Many of these devices are going to be mobile. They'll be deployed in places where, just quite frankly, wired power isn't feasible, or they're going to need to be on a device that's moving all the time. So relying on batteries is going to become both an environmental and an operational issue. So, clearly, I've read the various marketing reports where folks talk about, with 100 billion batteries needing to be replaced in the next in the coming years, that's going to fill so many, hundreds of Olympic swimming pools and things like that. But the bottom line is that, it's an incredibly wasteful and an environmental, disaster that's pending if we are going to wind up throwing out and disposing of so many batteries. But it's also an operational issue. So, we talk to many customers that actually look more at how frequently they have to go and replace the batteries on devices. And let's just say you have a few billion IoT devices out there with a 3-year battery life. That means you're going to be replacing on the order of 2 million batteries every day. And that is just a big labor expense as well, especially if you have commercial industrial applications where maybe the devices are just not so accessible. So we propose energy harvesting as a potential solution to this. And there are many energy harvesting products that are out there in the market today across various commercial, consumer, and industrial segments. The products generally can fall into two categories where they can either be entirely battery free, and we'll talk about things like mechanical harvesting switches, or certainly one of the cases folks are very aware of are RFID and security badges and cards that don't have batteries but are stimulated by RF energy. But then there are also devices with rechargeable batteries in them where they're relying on PV or even thermal harvesting to be able to charge up the battery for the long-term usage. And there you see things like solar-powered keyboards. We're going to talk, and we talk about thermal harvesting, and a company there that's actually developed a watch technology that uses thermal harvesting from the body. And last in the lower part of this is a PV-enabled remote control that was launched by Samsung earlier this year. A TV remote that has a rechargeable battery inside of it, but is charged entirely by PV. I should also point out that energy harvesting is not an all or nothing kind of proposition. So even just extending the battery life, I mentioned the maintenance costs of having to go and switch out batteries. If you can extend the battery life from something like 3 years to something like 5 to 7 years, now you've just effectively have the maintenance costs for that kind of product. So there are some definitely real benefits, and there's there is a history of various energy harvesting products out there in the market. And One I think that was interesting to highlight as I was researching for this talk is, everybody's familiar with the desktop calculator, and that for small calculators, we've used PV cells to eliminate batteries from them, and that was enabled by technology advancements both in the semiconductors, driving, doing the computation, but also the lower power consumption displays. But if you think about it, we've actually had energy harvesting calculators for much longer. The adding machines that we were using 100 years ago relied on mechanical energy harvesting to the user would have to type in the numbers and pull the crank in order to see the numbers get added up on a piece of paper tape. So certainly a long history of using energy harvesting. So let me talk about the 4 techniques that we're going to get into. We'll go through them, a little bit one by one here. So obviously photovoltaic harvesting, the first one I want to talk about, I think, is probably the one that most folks are familiar with or have seen. We'll talk about mechanical harvesting from the perspective of pushing a button, kind of application that could be for switches or simple remote controls. Thermal harvesting is something that maybe not many folks are familiar with. It's actually a technology that's been around for a long time. And then the last topic that we'll talk about is radio frequency harvesting. And what can you get from the energy that's out there from all these other wireless devices that we have. So first, let me talk about photovoltaic harvesting. So obviously where there's light, there's energy. And I think it's important to just highlight that whether it's indoors light sources or the outdoor sun, there are many examples of commercial products today, and we're seeing more and more PV being added into beacons, sensors, and tags for various IoT applications. But PV, one of the things that's happening, there's a lot of new technology being advanced in the market today. So it's not just about the kind of silicon substrates, the big PV panels that you see on people's houses, or even the small silicon cells that have been used in calculators and other products for years. There are now new materials like dye sensitized and even organic materials that are really viable options that have equivalent performance, or in some cases maybe even superior performance if they're tuned to maybe indoor light levels or higher indoor light levels and moderate outdoor light levels to be able to address specific applications. The other thing that you see from the photovoltaic harvesting is features like flexible substrates and custom form factors. So some of these new materials can literally be custom printed onto flexible plastics or other materials, and can make adding PV into an existing application easier if, let's say, there isn't a flat surface or you're trying to adapt it into an existing industrial design. So these are the kinds of things that are going to make it easier for folks to add PV to products and also see the performance. So the question obviously comes up is, how much energy can you harvest from PV? So first, let's talk about light levels. And light levels are generally measured in lux, and lux levels can vary from something very small, so a very dim room can be 50 lux, where it's hard to, you wouldn't want to try to read by that. It might be something where you're watching TV in a very dimly lit room, all the way up to what's a bright sunny day, which is over 100,000 lux. And so obviously the amount of energy that you can harvest is going to be specifically proportional to the amount of lux. So you can see in the table on the right here that I'm giving folks an idea of the range of energy that's available, and we're talking about microwatts per square centimeter for these different kind of light levels. So going from something that's a dim indoor light level, 200 lux, which you might see in a kind of a typical home environment. When you get into the office or a bright retail environment, you're going to be 500 up to 1,000 lux. Then when you get to sort of a full kind of outdoor daylight during the day, you're in the tens of thousands of lux, all the way up to literally putting something in direct sunlight where you could see 100,000 lux. The important thing to keep in mind here is that there's obviously variance in performance for PV cells based on their technology and also their optimal performance range. So some are certainly much more optimized to work better in low light conditions, and where they actually, putting them outdoors could cause long-term damage to the cell. Where there are other cells that perform very well in higher light levels or outdoor light levels that will literally shut off when you get to dimmer indoor light levels. So there's a range when you're looking at selecting PV cells to think about the conditions that they're going to be operating in, and then also what the efficiency needs are. You can see from some of the ranges that are listed in the table, it can be a factor of 2, 4, or even more in difference between different technologies at different light levels to the amount of energy that you can harvest per square centimeter. And some of these more efficient cells are obviously going to be things that are potentially much more expensive. So when we look at PV applications, it's very important to factor in what is the lighting profile of the environment that you're going to be in, with the product that you have, what is the amount of available area that is going to be there for a PV cell to be integrated into the product, and also what is your budget. There are certainly, there are technologies I didn't mention when I was talking about technologies like gallium arsenide, which can be quite expensive, but are very efficient and can come in very small, compact packages. So these are the kind of factors, and we'll revisit PV technology again when we come to the very end of the presentation and we talk about an actual application and the kind of numbers that you can expect from PV. So let me move on now to mechanical harvesting. With mechanical harvesting, in this case, we're looking at generating energy from mechanical harvesting that is an actuation of something like a switch or a button that's creating a burst of energy. And you can see on the top right here, the types of harvesters we're talking about is where that mechanical motion is moving a magnet through a coil to create these sort of burst patterns that you see on the plot on the lower right there, which is some actual data that we've taken across multiple types of harvesters. And in the time, you get a very brief, just a few millisecond burst of energy from that magnetic coil. And that energy is then got to be captured, and it's actually sufficient energy to be able to be used for multiple wireless transmissions. So the combination of having a mechanical harvester plus some of the very low power consumption for wireless devices enables you to create something that's truly battery free. And so to do this in an actual mechanical harvesting application, the type of switch, you're not going to be storing that energy in a battery. You're going to be using it immediately. So there are mechanisms, the mechanisms I was showing on the previous slide are available that can harvest energy on both a push and a release. So you can have a switch where you can do a push and hold for, say, a dimming light control versus a push and release immediately, where you'd sort of have the equivalent of kind of an on-off type of behavior. So the applications for this, there are certainly products out there on the market, like I talked about, wall switches, very simple remote controls. The product in the lower right is just a simple one button, long distance remote control done with mechanical energy harvesting. Doorbells is another potential application where you might want to be putting a doorbell in a location where you don't have a wiring available to power the doorbell. So it's just far easier to use mechanical harvesting in this application. The challenge, obviously, with mechanical harvesting is you do have a mechanical harvesting element. The elements I was showing on the previous slide are probably about 1 inch or 3 centimeters on the square, maybe less than a centimeter thick. But you still have to figure out how to integrate that into the button. And then how many buttons are actually going to be able to be rigged to be able to support that one harvesting mechanism. I've seen designs with even 4 buttons on some of those wall switch designs. So, but it's certainly a very applicable technology for some applications. So let me move on next to thermal harvesting. Thermal harvesting is something that may not be well known to a lot of people, but it is possible to harvest heat energy with what are called TEG, or thermoelectric generation devices. This phenomena was actually discovered over 200 years ago, that by putting together materials with, you can see in the top right here, specific P and N doped materials, that it's possible to get either electrons to flow in different directions by applying heat to one side and having a heat sink, or having a cold side on the other side of a flat surface. So the bottom right here shows an example of a TEG device, and you can see the comb of material that's in the middle between 2 plates there. That material is what's actually being heated on one side and chilled on the other side. Generally, these types of thermal harvesting devices are going to generate pretty low voltages, so the potential is going to be in the tens, maybe 100 millivolts. So you're going to need boost circuitry to be able to provide something that's going to be usable for a typical integrated circuit that's going to want to operate in, certainly well above a volt. So while the technology has been around for quite a while, it's only recently that we've seen some advances with some modular type solutions. This is an example of a solution from a company called Matrix Industries, which has created a TEG module that includes the boost circuit. So it can actually be connected directly to a device, to a semiconductor device to power it, or to an energy management circuit. So a module like this is going to be you can see there, it's about 18 by 30 millimeters by roughly half a centimeter thick. So, maybe the size of roughly an oversized postage stamp, but with just a small 10-degree temperature delta, you can generate, 800 microwatts of power from it. And you can see the graph on the lower right here really shows how the amount of energy increases as you're able to increase that temperature gradient. So you can get quite a bit of power with enough of a temperature difference. So for applications like motors or furnaces or other heat generating equipment, or even the human body. I mentioned earlier on that Matrix actually worked with a company to develop a thermal harvesting wristwatch, which was able to completely support the energy requirements that would be needed for a basic watch function using the heat from your wrist. So it's important to also remember, though, in the midst of this, that you not only need to have a heat source, but you need to have a heat sink for one of these modules to be effective. So that heat sink, whether it's an additional piece of metal, or in the case of the watch application, it was actually the body of the watch was being used as a heat sink, to be able to move that heat, because the heat has to continuously flow through that TEG device to be able to have a continuous source of current and energy coming from it. So that's generally been the challenge with these types of solutions, that you need to figure out how to integrate and attach to the heat source, and then how to have the appropriate heat sink to be able to move the heat energy away. Okay. The last technology I want to talk about is RF harvesting technology, and specifically go into a little bit of a deeper dive about radio frequencies and energy harvesting. So to be able to harvest energy from a radio, there's obviously got to be some kind of RF source that's out there. And we'll talk in the next slide. I'll show a little bit of more information about, for some different frequency bands, what kind of regulatory considerations what specific frequencies are available, what are the maximum power output available in these bands. So that's going to define the limits of what kind of RF source you can have. And then as the radio waves move through the air, their path loss is proportional to 1 over the frequency squared and the distance squared. So what that means is you're going to have higher path loss, obviously the farther away you move from the source, and also the frequencies at which you're operating. So I'll also show some contrast of the amount of power that's available as you look at different frequencies and power levels. So it's important to keep in mind when we talk about RF energy, the different power levels that are really available. When you think about a wireless device, let's say it's your cell phone or a Bluetooth or a Wi-Fi device, they're going to be receiving power well below minus 60 dBm at their antenna to be able to pick up information. So you can see minus 60 dBm, that's a nanowatt. Minus 30 dBm is a microwatt, and a microwatt is, even then, to be operating a circuit, when you think about an RF transceiver, is generally going to be operating in the milliwatts to a watt kind of range. So 0 dBm is a milliwatt, and 30 dBm is a watt. So when you talk about a watt transmitter, you're talking about having to accumulate a lot of energy from an RF source to be able to do that. So that really is the challenge with RF harvesting, is the amount of energy and the steep drop off that happens as you move away from the RF source can make it challenging to harvest energy at a distance, and I'll talk a little bit more about that. The other factor to keep in mind is when you are harvesting that energy, it's the amount of energy that you can get is also going to depend on the sensitivity of the receiver and the efficiency of both that harvester and whatever storage element you're using to harvest that energy. So just because the physics and the equations tell you that there's a certain amount of energy that's going to be available at a certain distance from an RF source, doesn't necessarily mean that all of that energy is going to be accessible to you, because there are going to be efficiency limits that you're going to have to deal with, and we'll cover that in a few slides as well. So let's talk about those regulatory limits. And we like to, when we talk about RF harvesting, we like to separate it into two specific bands. So a sub-gigahertz band, generally 850 to 930 megahertz. You can see from the table on the left how the requirements for that band is changed based on the geography you're in. So in North America and some parts in Japan and other places, you can have actually much higher transmit powers, especially when you compare to the limits for the 2.4 gigahertz band. The 2.4 gigahertz band, obviously, most folks are familiar with from Bluetooth and Wi-Fi and the other technologies, Zigbee, that operate in the 2.4 gigahertz band. The sub-gigahertz band is frequently used for some cordless phone applications, baby monitors. It has obviously the advantage of being lower frequency, so it is going to give much better range. So there are a lot of IoT applications as well, other radio networks that operate in the 900 megahertz band as well. But you can see the challenge here is that while you have the higher transmit power limits, the frequencies are not universal worldwide, and you have to pay attention to what those limits are. The 2.4 gigahertz band, much more universal, but there are some very strict power limitations, especially in places like Europe, where you have 10 dB less power in general available. And so those limits do have an impact in the amount of energy that you're going to be able to see. So when we look at just from a pure mathematical, we look at the physics, what's the maximum theoretical power that you can get versus distance for 100% duty cycle RF source, you can see from the plot on the right how that energy falls off rather quickly, especially for the 2.4 gigahertz signals that you see there in blue and in red. So really moving much beyond a meter. You're with 2.4 gigahertz, even just the raw amount of energy that's available is going to be less than 100 microwatts. And then you have to factor into that the efficiency of the harvester and the storage, which probably best case could be maybe 75%. But if depending upon the energy storage method you're using, it might drop you down to 50 or even 40% efficiency. Again, it depends a lot on the application and the harvester and how the storage needs to be done. So when we think about 2.4 gigahertz operation, we're thinking about things that are much closer in terms of being able to harvest energy. So the other thing to keep in mind about 2.4 gigahertz as well is you're sharing that band with other devices. So high duty cycle 2.4 gigahertz transmissions, could be interfering with Bluetooth or Wi-Fi or the operation of other devices. So we generally want to be careful when we talk about the using 2.4 gigahertz for RF energy harvesting. You can see here the 900 megahertz band. These curves are based on 915 megahertz, but you could expect kind of comparable results with the much higher power levels and the lower loss. We can definitely provide energy, well out past 2 to 3 meters that you see here, but even harvesting, well out past 5 or 6 meters is certainly possible for some applications, and we'll have an example of an application coming later. So the challenge you can imagine here, there's a lot of 2.4 gigahertz devices that are potential sources out there, but what about 900 megahertz sources? And I want to take a little bit of a pause here to talk about standardization around some of this RF transmission. So there's a group called the Air Fuel Alliance, which is an alliance of over 50 electronics companies, universities, research institutions that are working to develop a standard for RF charging, or what you might call wireless power transfer. So being able to set up a dedicated RF source in the sub-gigahertz band to be able to do that wireless power transfer to multiple target devices. And so the standard focuses on being able to have flexible device placement, being able to get that longer range that I talked about from these sub-gigahertz devices, and then uses the portion of the band that's available based on the in-country regulations, like I was describing before. So this is something that has to be adjusted based on your geography, and the technology is also going to be using Bluetooth to enable discovery and control of the devices. So the source, while it's got a 900 megahertz radio, it's also going to have Bluetooth so that devices can actually find it and tell it to turn on its source and to manage the activity of the source. So a little bit about practical considerations for RF harvesting. Just to sum up, you need to have a consistent source. So ambient harvesting of RF is very difficult. Even if you were to find be in an environment with, say, a regular source of Wi-Fi energy or cellular energy, you're going to be talking about nanowatts of energy that's going to be available. So a 2.4 gigahertz source, you're going to need to be, it needs to be active. It needs to be turned on and close by. One of the things about your Wi-Fi access points is that they're trying to really optimize their data transmissions and transmit as much as possible. So they tend to try to transmit it at higher data rates and keep their duty cycles as low as possible. Sub-gigahertz bands, they offer more power, but are not geographically consistent in terms of the frequencies available. So dedicated sources are going to be your best bet to be able to have control and consistency and give a better user experience. So understanding the use case, does the application need a battery? So is the device something like a security badge or a tag that only needs to be active when it's in proximity of, say, an RF reader? You think about like an RFID kind of use case. Will the device be operating when it needs to be harvesting? So another use case potentially for RF is to be able to recharge devices when they're not operating, whether it's a type of a recharging, putting multiple devices in a box or bringing them in very close proximity to a source. And how close can you get the device to the source? So applications where you maybe need to reading at a range of multiple meters, you have to factor in the amount of power that can actually be available there. So that's some overview of four of the harvesting methods that we at Atmosic are focused on. And I wanted to take a few minutes before we wrap up here to talk about Atmosic technologies and how we look at energy harvesting. And the product that Atmosic has that's focused on energy harvesting applications is a very low power Bluetooth SoC. So this is a chip that we manufacture that's available today. It's the lowest power Bluetooth 5.0 SoC out of the marketplace. You can see some of the specs there on the right-hand side in terms of the active, receive, and transmit power. It also has a number of features to help optimize low energy performance. It has a separate on-demand wake-up receiver that can be used with a separate RF signal to be able to keep the chip in a very, very low power state and only wake it up when it sees a certain specific RF pattern. And it performs something called managed energy harvesting, which I'll get into in the next slide in much more detail. There's also a sensor hub, which allows us to read sensor information from an external sensor, again, keeping the rest of the chip in a very, very low power state and only wake it up on exception. There's integrated RAM and ROM, and we also support a flash option with this chip. And there's multiple packaging options to support all of the various interfaces that are necessary for sensor, keypad, keyboard, and other applications for it. So this is a fully Bluetooth qualified part and is shipping today. And I want to highlight some of the unique features of this part. So certainly the low power consumption is very important because, as I mentioned earlier, it's been some of these advances in the lower power wireless devices that have allowed energy harvesting to become something that's feasible, so that you don't need to have a PV cell the size of a keyboard in order to harvest enough energy to operate a wireless keyboard. But the other feature that I want to highlight is the integrated power management unit. So the power management unit that's part of this device is actually able to harvest and manage multiple energy inputs. So you can see from the graph here, the block diagram on the right, there is a separate RF input for an integrated RF harvester, which is built onto the device. And there's a matching network that can be tuned to frequencies between 400 megahertz and 2.5 gigahertz in order to facilitate the harvesting of the appropriate band. And then there's a separate external harvester input, which can be used for the PV, mechanical, thermal sources. And the power management unit takes the energy in from those harvesting sources. It can use it immediately to power the Bluetooth and the rest of the chip, or it can put that energy back out to a storage capacitor or even a rechargeable battery. And the power management unit is always working to prioritize energy requests across the available sources to maximize battery life. So always using harvested energy first, then using stored energy second, and then finally defaulting to a battery. So what does that look like for practically in different storage configurations? So we can actually implement a battery-free device by using either a regular capacitor, a storage, a supercapacitor to store energy without any kind of battery. And that energy storage is obviously going to be temporary, but it's good for applications that have either a consistent source of energy, or, as I mentioned earlier, they might be doing something like an on-demand operation, like an RF security tag, which is only going to be active when it's has RF energy applied to it, or something like a photovoltaic beacon sensor that is just going to be active when there is light on. But we can also use energy harvesting to extend the battery life. So by adding a battery, using the storage cap, and the way that the power management unit prioritizes those energy requests, we can develop longer lasting products, or be able to use a smaller battery and have the same battery life as an existing product. And then finally, there's the scenario of actually getting the battery to last forever. And maybe I should put forever in quotes there, because there's no such thing as a battery that lasts forever, but being able to use harvested energy to recharge a rechargeable battery through the power management unit. The other thing I'd like to highlight is the difference and the benefit that we gather from having that PMU integrated into our device versus maybe a typical energy harvesting solution where there's an external PMU. The harvested energy solution is going to be harvesting and storing that energy prior to it being able to be used. So it adds an additional component, and it's going to lower the overall efficiency because you have to go into and out of storage. Whereas the Atmosic solution, the integrated PMU, not only reduces the bill of materials, but we can also use that harvested energy directly without having to put it out to storage. And that then highlighting the low power consumption of our Bluetooth extends the energy harvester performance. So that means you're either able to use the same amount of energy better, or you can move to a smaller size harvester, let's say in the case of a PV cell. So how does this look in a practical application? And I'll just wrap up by giving one simple example, but there's obviously many more potential examples. So let's say you're working on a Bluetooth beacon that's going to be trying to use harvested energy, and you could use a 5 to 7 square centimeter PV cell, and with the low power consumption of the Atmosic Bluetooth device at 200 lux, which is a typical relatively low indoor light level, a small PV cell is going to give you enough energy to support a once per second beacon. So this is something that's going to be on the order of tens of microwatts of sustained energy that's required. Likewise, for mechanical energy, just one button press provides enough microjoules to be able to generate 10 beacons. With the type of thermal harvesting application that I was describing earlier with the Matrix module, just a small 5°C temperature gradient can support that, again, that once per second beacon, being able to generate those tens of microwatts that are required to keep that beacon consistent. And then likewise with a 900 megahertz 36 dBm source, which is really pushing the limits at 100% duty cycle, you'd be able to sustain that beacon well out past up to 5 meters. So there's certainly plenty of ways to be able to use energy harvesting, and this is just a simple beacon application. Obviously, different applications if you wanted to add sensors or other application functionality, that's going to make the power consumption go up, and it would factor into whether it be the size of the PV cell or the temperature gradient required, or the proximity from the RF source that you would need. But these are all things that can be factored into the application design when you select and the selection of the energy harvester that's going to be used. So let me just wrap up here. So energy harvesting offers a great potential solution to battery waste and device maintenance costs for the many IoT devices and all kinds of devices that are going to be out there. There are certainly multiple energy harvesting technologies available. They're not, certainly not one size fits all. So understanding the environment and the application is critical. And lastly, to sum up, Atmosic combines their very low power Bluetooth solution with an integrated energy harvesting power management unit, and that can really help customers both get a high performance solution, but also at a cost-effective price point. So I'd like to wrap up here, and I'll send it back over to Will to monitor and MC our Q&A session. Thank you.
Thank you very much, Paul. Appreciate that. We do have some questions that came in. We'll go through those one at a time. If you have additional questions, please insert them in the text box on the right. So our first question is there enough RF energy in an urban environment to harvest these from these devices? So Paul, would you like to answer that question? Or Paul Husted, maybe? Paul Davis, do you want to answer that question?
Okay. Yeah. So I'll just say that, in a typical urban environment, as I mentioned, you're going to be, again, it all depends on proximity to the source, but you're going to be seeing, nanowatts or fractions of nanowatts in the air. So the amount of energy that you're going to be able to harvest just wandering around with a harvester device is not going to be sufficient to power a wireless sensor or anything like that. So I know that's might be one of the misconceptions that's out there, but you really need to have a source, and the proximity to the source has got to be on the order of a few meters, depending upon the application and the frequency band. So I think that's something that's very important to highlight here.
Okay, we've got a question about, do you have tested your RF harvesting stage in a real ambient harvesting application to charge a capacitor during a long period to send sensor data?
Yeah, so we have customers that have done this. I should mention that Atmosic has an evaluation platform with an RF source, a 900 megahertz RF source that we provide to allow customers to explore the performance, with range and in that frequency band. And with that evaluation kit, you can attach sensors to it and prototype, the type of application, and you can get a feel for the amount of energy and the amount of range required. I mean, obviously not all sensors are different in terms of their power consumption needs. But yes, we do have some customers that are actively developing RF harvesting applications for commercial and industrial sensors that will be battery free and will be relying on RF harvesting to report back sensor data.
Right. And do you have a reference design for mechanical harvesting applications, the wall switch, for example, using the M3?
So we do have, when you say a reference design, we do have a schematic that we've developed. As a semiconductor company, we're not in the business of doing industrial design and things like that, but we certainly have been able to demonstrate with different harvesters and circuits the amount of energy. You saw the curves that were in the presentation. That was actually from some internal data that we've taken. We do have some switch vendors that are developing products already. So if that's something of interest, I'd encourage you to reach out to us, and we can work to put you in touch with some of the folks that are actually building product with the Atmosic technology and energy harvesting.
So another question that I'll answer said, is there a Bluetooth 5.2 SoC with RF energy harvesting available from Atmosic? So yes, that is available. So the person that asked that question, we can reach out to you separately and provide that information. Next question on RF harvesting is, can the on-chip harvester be tuned dynamically or statically via firmware?
You want me to take that?
Yeah, Masoud, that'd be
I can take a stab at it. So the harvest, there is a matching network, external matching network on the board that kind of tunes the harvesting antenna to the harvester. So as wide as that matching network is, essentially, that defines the bandwidth of your harvester. The on-chip harvesters are wideband, but the bandwidth will be limited by the external matching network. So for a particular frequency, you need a dedicated matching network that selects that frequency. Now, hypothetically, and I'm just talking hypothetically here, if you can program your matching network in a smart way using GPIOs and all that, to tune it to a different frequency, yes, you would be able to do that. But keep in mind that to get the most out of your harvester, your matching network needs to be very well fine-tuned to your harvester at that particular frequency. So for all practical purposes, the frequency will be defined by the matching network, and it cannot be dynamically changed.
Thank you. Next question is there a column counter in the PMU to be able to gauge cumulated harvesting power?
Sorry, can I repeat that question again?
Masoud, so yeah, is there some way to gauge the amount of energy being harvested inside the PMU?
Yeah, so I guess on our second generation, we have a way of telling if there is enough energy, how much harvested energy we got on the capacitor, and that could provide you a gauge.
Yeah, there is the ability to the PMU is looking at voltage levels. So it does know, for instance, when a supercapacitor is fully charged up to 3 volts and things like that. So while there isn't the Coulomb counter functionality isn't there, there is some gauging of the stored energy that is done by the parts. So it knows when it's being depleted and it knows when it's you can set triggers based on analog voltage levels.
And that's an important point because it provides a key advantage of our solution, because we provide the connectivity, the Bluetooth connectivity, as a backend connectivity as well. So if the device is running out of energy, it can use the Bluetooth connection to the source and tell the source that, hey, beam some more energy towards me, I'm running out.
Okay. And another question: is it possible to maintain the Bluetooth low energy connection, not just transmitting advertising packets, from pure energy harvesting with no battery? So can you maintain a true BLE link essentially with no battery using energy harvesting?
So the answer is yes, it's always possible with enough harvested energy. So maintaining a connection definitely does require a lot more energy than just doing advertising packets. But as I was mentioning, you can do it without a battery. Generally, what you're going to need in most cases, you're going to need some sort of supercapacitor type of storage to be able to have enough energy on hand to deal with the peaks that occur when you're doing a transmission. So the amount of storage that you might need will change. Again, it depends on what the connection is and how long it needs to be maintained. But we certainly have some applications where with enough storage, we've been able to do a very low, a long interval type of connection. So maintain a connection where just a few packets are going across every now and again.
And last question is, in addition to energy harvesting, is there an input to charge a battery from a source such as a USB connection?
On our second generation product, there is, yes.
So that's it for questions today. This wraps up the webinar. So thank you everybody for attending. I hope this was useful, and we look forward to having you join our next session. All right, thank you very much.
Yeah, thank you everyone.
Thank you.